Good evening and welcome to my channel. Today we'll be continuing our lecture on direct current circuit analysis. In the last lecture, we looked at a Kirchhoff current law, mesh current analysis, nodal voltage analysis, and Thevenin theorem. In the lecture of today, we'll be looking at Norton theorem, superposition theorem, star delta transformation, voltage divider, DC series and parallel circuit, combination of series and parallel circuit. Taking you through this lecture is Engineer Binoba, lecturer, Federal University of Petroleum Resources. Happy listening. Norton theorem. Norton theorem states that any linear circuit containing several energy sources and resistances can be replaced by a single constant current generator in parallel with a single resistor. So if you have a circuit arrangement containing more than one sources and more than one resistances, it can be reduced into a single current source in parallel with a single resistance source. So this is the equivalent Norton circuit. Then you introduce your load resistance in order for it to carry out any form of calculation. So we take an example to illustrate that particular theorem. So this is the question. The question says that using Norton theorem, find the current flowing through the 40 ohms resistor. So we proceed. To find the Norton equivalent circuit, we first have to remove the 40 ohms load resistor and short out the terminal A and B to give us this particular circuit. So the first thing we need to do is to calculate our Thevenin Norton current. So to do that, we remove the load resistance and replace it with a short circuit. After doing that, we are going to have this particular loop and this particular loop after shorting. So it's easy for us to calculate the current flowing through this particular loop. We refer to it as I1, and we can also easily calculate the current flowing through this particular loop. We refer to it as I2. So after calculating the current flowing through this point, calculating the flowing through this point, both of them, I1 will move through this point and I2 will move through this point. So we now add both current together to get what we call the short circuit current at this point. So I1 is equals to the voltage supply, which is 10 volts divided by your resistance 10 ohms. So the current flowing in this particular loop is 1 amp. Then we go to this loop. Current I2 is equals to your voltage all over your resistance. Again, the current flowing to this particular loop is equals to 1 amp. So by the time this current come or move down, this current come move down, we have the short circuit current to be equals to I1 plus I2. So the short circuit current in this circuit is equals to 2 amps. Then the next thing we need to calculate is our equivalent resistance. In order to do that, we open circuit we remove the load resistance and replace it with a open circuit and short circuit the two sources. When we do that and we come to this point, looking at this point into this particular node, we discover that this resistor is in parallel with this resistor. Remember, you are moving up. So when you get to this point, part of your current is going to flow to this part, part of your current is going to flow to this part. That is making this and this to be in parallel. So to calculate our equivalent resistance, we now have a product over sum, which is 20 times 10 divided by 20 plus 10. So our equivalent resistance is equals to 6.67 ohms. So we have calculated our short circuit current and our equivalent resistance. So we now get what we call the Thevenin circuit. So this is the Thevenin equivalent circuit of that last circuit we started with. So after doing that, we now introduce our load resistance. When you now introduce your load resistance, you will discover that at this point, any parameters you wish to calculate, you can calculate. The question says we should look for the current flowing through this 40 ohms resistors. Remember, the current coming from the source is equals to 2 amps. So by the time it gets here, part of it is going to flow through this 6.67 ohms resistor, and part of it is going to flow through this 40 ohms resistor, making this resistor and this resistor to be in parallel. But it can easily be calculated using what we call the current divider. So applying current divider rule here to get the current flowing through the load resistor is simply equals to I arrow L is equals to arrow S, which is your equivalent resistance, times your short circuit current IS divided by your equivalent resistance plus your load resistance. So when you do that, you are going to get I arrow S equals to 0.286 amps. Exactly the same result we got when we are calculating using other basic principle. So in summary, the basic procedure for solving a circuit using Norton theory is as follows. 1. Remove the load resistor or component concerned and replace with a short link. After you've done that, you find IS by adding all the current flowing through the load. After you've done that, you find ROS by short-circuiting all voltage sources or by opening circuit all current sources. After you've done that, you find the current flowing through the load resistor that is required in the circuit. So those are the basic things you need to do in order to apply Norton theorem in solving a particular circuit. So we now look at superposition theorem. Superposition theory states that the total current or voltage at any point in a linear circuit with multiple voltage or current sources is the algebraic sum of the current or voltage produced by each source acting independently while all other sources are deactivated. This simply means that if you have a circuit containing more than one voltage sources, it is easier for you to analyze the circuit. All you need to do is activate one voltage source at a time and find different parameters, especially the current flowing through the circuit. After that, you deactivate that particular voltage source, you activate another, taking into consideration the direction of current. And when you are done with all your analysis, you can now add all your values of current together in order to get a current at a particular node. So in order to understand that better, let us try and see how we can use this example again to explain that. Okay, find the current flowing in the 40 ohms resistor. For us to do that, so I can see when the current leaves the 10 volt source, we call that current I1. The current leaving the 20 volt source, we call it I2. And the current coming into the 40 ohms resistor is called I3, which is equals to I1 plus I2. So remember, the question says we should find the current flowing through this particular resistor. So as the law says, we apply the law by taking into consideration each source while deactivating the other source. So we look at it. So to start with, we deactivate the 20 volt source by replacing it with a source circuit. So when we do that, this is exactly what we are going to get. You discover that this resistor and this resistor will now be in parallel. So after doing that, we have a current here, I1, flowing through the circuit. I1 flowing through this circuit. So the first thing we need to do is to look for our equivalent resistance. After doing that, we can now calculate the total current flowing through the circuit. So to do that, we come here, arrow equivalent. We already know that the 40 ohms resistor and the 20 ohms resistor, they are in parallel. So first of all, resolve them in parallel. So we have that Arrow equivalent is equals to R2 times R3 all over R2 plus R3. And when you do that mathematics, you are going to get the equivalent resistance as 13.33 ohms. So after that, this particular resistor will now be in series with this particular resistor, making our total resistance to be equals to 10 ohms plus 13.33 ohms, making it to be 23.33 ohms. So now the current flowing through this part, we can call it I1 prime. I1 prime, because from the initial circuit is written as I1. So at this point we call it I1 prime. So I1 prime here, which is the current flowing through this circuit, is equals to the voltage in the circuit divided by the equivalent resistance, which is giving us 0.29 amps. So our I1 prime is equals to 0.429 amps. So what is left now for us to calculate the current flowing through the 40 ohms resistor and the current flowing through the 20 ohms resistor. So at this point, we refer to the current flowing through the 40 ohms resistor as I3 prime, and we refer to the current flowing through the 20 ohms resistor as I2 prime. So we apply a current division law again in order to do that. So the I2 prime, which is the current flowing through the 40 ohms resistor, is I2 prime, which is the current flowing through the 20 ohms resistor, is equals to I1 prime times I3 all over R2 plus I3. So for us to look for the current flowing through this particular resistor R2, we multiply the current, the R3 by the current flowing through the circuit, which is I1 prime prime. So when we do that, we get our result as 0.286 amp. Also, for us to calculate the current I3 prime flowing through the 40 ohms resistor, we multiply the total current flowing through the circuit, which is I1 prime, by R2, then we divide it by R2 plus R3. So when you do that, you get this particular equation. So you discover that for this first part, after shorting the 20 ohms resistor, we're able to calculate our current I prime prime, I2 prime, and I3 prime. So the result we get, we keep it, taking note of the direction of current. So like you will see, this particular current I1 is flowing from your left, from the source to your right, while the current entering this place is also flowing from node A to ground, while the current flowing through this part is also flowing from node A to ground. So you can see the direction of current moving from up to down. So you take note of those directions and their values. Then the next thing you go to the same circuit and now short your 10 volt source and find the current, total current flowing through the circuit and the equivalent resistance. So when this is shorted, discover that this particular resistor R3 and R1, they are in parallel. So when you resolve them in parallel, you add it to this 20 ohms resistor, you are going to get the total equivalent resistance. So when we do that, we discover that our total equivalent resistance is equals to 28 ohms. 28 ohms. When we resolve this in parallel and we resolve this in series, we are going to get 28 ohms as our total resistance. After I've gotten our total resistance, it is easy for us to find the current flowing through the circuit. So at this point, we call the current flowing through the circuit I2 prime prime, which is I2 prime prime, which is the total voltage divided by the total resistance. When we do that, we get 0.714 amps as the total current flowing through this circuit. After we've gotten the total current flowing through the circuit, we now come back to this circuit to calculate the current flowing at each of these points. So this is the circuit. When we do that, we also apply the current divider rule, knowing that the current flowing through this particular point is I3 prime, while the current flowing through this particular point is I1 prime prime. So the current flowing through this part I3 prime prime is equals to the supply current I2 prime prime times resistor R3 divided by R1 plus R3. When you do that, you get 0.571 amps. Also, the current I3 prime prime flowing through this point, you take this is R1 times the total current flowing through the circuit, which is I2 prime prime, divided by R1 plus R2. So when we do that mathematics, we are going to get our current as 0.13 amp. But our point of interest is the current flowing through the 340 ohms load resistor. So it is easy. We know that the current flowing through this point is I3. So we have calculated for I3 prime and I3 prime prime. So what we need to do, when we look at them, both of them are moving in the same direction. So that tells us that I3 prime will now be equals to I3 prime plus I3 prime prime, since both of them are moving in the same direction. And when you add up that, you are going to get I3 to be 0.286 amp. Exactly what we got when we applied the Norton theorem and calculate the current flowing through that point. In summary, the basic procedure for solving any circuit using superposition theory is as follows. Identify all the independent sources in the circuit, such as the voltage source and the current source, and select just one source in the circuit at a time to analyze. Turn off short circuit or open circuit all the other independent sources and analyze the circuit using only one active source. Number 3, use standard circuit analysis technique, Ohm's law, Kirchhoff's law, to determine the voltage across or current through the desired circuit element, branch or node due to the single selected source. Then number 4, repeat each independent source one at a time, considering only the effect of that source while keeping all the other turned off. Then number 5, algebraically sum the individual responses obtained from each source to find the total response at the current circuit element, branch or node of interest. Then lastly, pay attention to polarities, sign conventions, and direction of flow of combined response when all the sources are acting simultaneously. So these are the basic things you need to know when trying to apply superposition theorem. Star delta transformation. Standard three-phase circuit or network take on two major forms. A star connected network which has the symbol, as we can see, star, and a delta connection network which has the symbol like a triangle, delta. If a three-phase, three-wire supply or even a three-phase load is connected in one type of configuration, it can be easily transformed or changed into an equivalent configuration of the other type by using either the star delta transformation or the delta star transformation. So a network consisting of three impedances can be connected together to form a T or T configuration, but the network can also be withdrawn to form a star or a star connection as shown in this part. So this is your T network. It has been transformed from the T to the star network. All you need to do is just take this one, you swing it up, take this one, you swing it up, and you are already having what is here. So you see this one, you swing it up like this one, you swing it up, and this is P and this is arrow. So you have transformed this T network into a star network. Also, you can also transform a pi network into a delta network. So you see your C, so you come to this point and just take it up, you are having this particular network. So if you have this type of network, you can easily convert a delta to a star and a star network to a delta. So let us now see how to transform. If you have a network given to you in the delta form, it can easily be transformed to the star form. You don't need to try to struggle with the formula. It's very easy to get. How do you do that? You want to convert this delta to star. Try and move this star and put it in between this point. You notice that your P will be here, your arrow will be here, and your Q will be here. So what do? To get your P is equals to AB. So you multiply this like this, all over A plus B plus C. So take note, your P is here. So just say AB all over A plus B plus C. Then again, to get your arrow, know that arrow is here. You have your BC all over A plus B plus C. Then to get your Q, you know that your Q is here, is AC all over A plus B plus C. Very easy. You don't need to struggle with the formula. Take it again. Know that your P is here. So to get your equivalent star, all you need to do is say A times B, which is this, all over A plus B plus C. Then again, to get your Q is just here. When you move this thing inside there, your Q will lie here. So it's equals to A times C all over A plus B to C. Then to get your arrow is the same thing, BC all over A plus B plus. So let us take a simple example to illustrate the conversion from a delta resistive network into a star network. For example 3, convert the following delta resistive network into an equivalent star network. So like we said, it is easy to do. To get your Q, know that Q is at this point. Q is at this point. So we say A all over C times A times C all over A plus B plus C. When you do that, you get this. Then to get your P is AB. So your P is at this point. So A times B all over A plus B plus C, you get this. And your arrow is at this point. So you have B times C all over A plus B plus C. I am going to get this as your result. Star to delta transformation. So you have a system given to you in star. You can easily convert it to a delta equivalent. It's very simple and straightforward. Again, you can place this particular star network into this point. So you notice that after doing that, at this arm, you are going to have your P and your Q, making A to be equals to P times Q all over arrow, P times Q all over arrow plus Q plus arrow. Very easy. P times Q all over arrow plus P plus Q. Again, to get your B, which is this point, when you place this and this, you have P times arrow, which is this arrow P, all over Q plus P plus arrow. Then indeed, to get your C, you know that C will be this and this, which is this and this. So you have a Q times arrow all over P plus Q plus arrow. As easy as that. So you don't need to stress yourself trying to see how you can struggle with the formula. With the simple diagram, you can easily just extract your formula. So let us look at an example. Convert the following star resisting network into an equivalent delta network. So by the time you apply the formula, this is your star network and this is your delta network. This is a simple formula. You can see that your A now is equals to QP, which is a P times Q all over arrow, which is this, plus Q plus arrow. You do that, you are going to get this. Also, your B is equals to arrow P, which is arrow P all over Q plus arrow plus P. You get your result. And also your C is equals to Q arrow all over P plus Q plus arrow, and you are going to get this, your result. Very, very straightforward. So moving forward, I'm going to look at our next topic, voltage divider. A voltage or potential divider is a simple passive circuit that takes advantage of the effect of voltage being dropped across components which are connected in series to produce a voltage which is fixed fraction of the source voltage. So voltage divider simply means that you have a source voltage and you have resistances arranged at different points in a circuit, usually a series circuit, in order to divide the voltage at different points. So that is what we refers to as a voltage divider. So voltage divider is useful to divide voltage into different voltage levels from a common source, as we said earlier. This voltage source can be a single positive or negative source. For example, we can have plus 12 plus 5 or minus 5 or minus 12 with respect to some common ground or node. So once you have a voltage source with respect to some common ground or node, you'll be able to get the voltage at different points in the circuit when they are connected in between different resistances. The potential meter, which is a variable resistor with a sliding cutter, is the most basic example of a voltage divider, as we can apply a voltage across each terminal and produce an output voltage in proportion to the mechanical position of each sliding contact. So a voltage divider is a very good example. When you put in your maximum voltage and you start rotating the slider, the voltage at where the slider stop, when you measure, it will be different from the voltage that is entering into the system. We can also make voltage divider using resistor circuit, capacity circuit, and using inductor circuit, as they are two terminal components which can be connected together in series. So you can, it's not only restricted to resistors, you can also make voltage divider using capacitor and using inductors. But for the purpose of this lecture, we are going to restrict our design using resistors. So voltage divider rule. The simplest, easier to understand and most basic form of a passive voltage divider network is a two resistor connected in series. This basic combination allows us to use the voltage divider rule to calculate the voltage drop across each resistor. So this is a simple circuit. You have your supply voltage and you have this resistor R1 and resistor R2 connected in series. So for you to calculate the voltage drop across resistor R1, all you need to do is you multiply your source voltage times R1 divided by R1 plus R2. Also, to calculate the voltage drop across your R2 resistor, all you need to do is multiply your source voltage times R2 divided by R1 plus R2. So that is a very simple way of looking for the voltage drop across a point. So let us take an example. So this is a simple circuit. So we should calculate the voltage drop across the 6 ohms resistor and the 8 ohms resistor. So it's very easy. So this is very easy. So this is the circuit. So to calculate the voltage drop at this 6 ohms resistor, VR1, you see your total voltage flowing in the circuit times your resistance R1 all over R1 plus R2. So when you do that, you get the VR1 to be 4.29 ohms. Also, to calculate VR2, you multiply your total voltage in the circuit times R2, then you divide by the summation of R1 plus R2. When you do that, you are going to get this. So note, when using voltage divider, we can see that the resistor with the largest value produces the largest voltage drop. So it's very easy. So when you are trying to apply the law in solving equation, take note, it is the resistance with the higher value that will produce the higher voltage drop. Like in this example, now the 8 ohm voltage drop is 5.71 and the lower voltage drop is for the 6 ohms resistor. So with this information, it's easier for you to know when you are making a mistake when solving or when you are getting the correct answer. So in order to apply this to a large circuit having many resistors, all we need to do, we try to take the voltage drop we want to look for, we multiply the total voltage flowing through the circuit times the resistor we want to look for the voltage drop all over the total resistance in the circuit. The first example we looked at was just an example with two resistors. For in cases where you have more than one resistors in the circuit connected in series, you can apply this particular law in finding the voltage drop across the individual points. This voltage divider equation can be used for any number of series resistances connected together because of the proportional relationship between each resistance, R and its corresponding voltage drop. So we'll take an example. Example 6. Calculate the voltage drop across each resistor given that Vs is equals to 15 volts. So when you have the source to be equals to 15 volts, you can easily calculate the voltage drop across R1, voltage drop across R2, voltage drop across R3. and voltage drop across R04. So to do that, first, your total resistance is equals to R1 plus R2 plus R3 plus R4. So since they are all connected in series, your total resistance R2 T is equals to 50 kilo ohms. Now to look at the voltage drop across the 8 ohms resistor, which is 8 kilo ohms resistor, which is R1, we have V R1 is equals to VAB is equals to Vs times R1 over RT. When you apply that into your equation, you have 8 ohms. Also, to calculate the voltage drop across R2, which is VR2, which is also VBC, is equals to Vs times R2 all over R total. When you do that, you get 4 volts. To calculate also the voltage drop across the 3 ohms resistor, you also apply that. So have Vs times R3 over RT, you get 2 volts. Then to calculate the voltage drop across the 4 ohms resistor, we have V R4, which equals to VDE equals to Vs times R4 all over RT. When you do that, you get 1 volt. So you notice here again that the resistance with the highest value have the highest voltage drop, which is equals to 8 volts. So take note of that very important information. Now we look at DC series and parallel circuit. DC series circuit. A DC series circuit or a series connected circuit is a connection of individual circuit components such as a resistor, capacitor, and inductor connected together end to end to provide just one current path. So it is clear from the diagram that these are resistors, they are connected in series. So when resistors are connected in series, the current through the resistors are the same and the voltage drop across the resistors are different. So when you add the individual voltage drop, you get your total voltage produced by your source. So we take an example to illustrate DC series circuit. Example 7. Calculate the loop current IT flowing around the circuit and the voltage drop across each resistor using voltage division rule. So the first thing we need to do in this circuit is to calculate the total current flowing through the circuit, which is referred to here as a IT, which is also IX here. So for us to do that, the first thing we need to do is to calculate the total resistance in the circuit. Since all the resistors are connected in series, all we need to do is just to add their individual resistance. So our total resistance is equals to R1 plus R2 plus R3 plus R4 plus R5. And when you add all the values, you are going to get 60 ohms as your total resistance. Now to calculate the total current, we apply Ohm's law. IT is equals to V over R, where your V is equals to your supply voltage 24 volts and your total resistance is equals to 60 ohms. And when you do that calculation, you're going to get your result as 400 milliamps or 0.4 amps as your answer. So the next question says we should calculate the voltage drop across each resistor using voltage divider rule. So as we earlier said before, in order for us to apply voltage divider rule in doing that, the first thing we need to do is to calculate our total resistance, and that we have calculated to be 60 ohms. So to calculate the voltage drop across this 5 ohms resistor is the supply voltage, which is Vs times R1 divided by the total resistance. So we have 24 divided by times 5 divided by 60, I'm going to get 2 volts. Again, to calculate the voltage drop across R2, which is VR2, is Vs times R2 all over RT. When we do that, we get a 4.8 volts. Again, VR3, we have Vs times R3 over RT, we have 8.0 volts if we do that. Then finally, VR5, which is this, multiplied by Vs times R5 all over RT, which equals to 24 times 8 all over 60, or 3.2 ohms. Again, we can notice from our solving that the resistance with the highest value have the highest voltage drop. So voltage drop across each resistor can also be calculated by multiplying the total current flowing through the circuit by their individual resistance as follows. So apart from using voltage divider rule, since you already know the total current flowing in the circuit, you just take the current and multiply it and the resistance, you get the voltage drop here. Since they are in series, the current that will flow through here is the same here, is the same here, is the same here, is the same here. So just take the current, multiply it and this resistance, you get the voltage drop. Do the same here, do the same here, do the same here, do the same here, and you get the voltage drop. By the time you have gotten all the voltage drop, if you add them together, you're going to get your answer as 24 volts. So that's exactly what this is trying to explain. So R1 is equals to I2 times R1, you get 2 volts. R2 is equals to I2 times R2, where I2 is the total current flowing through the circuit. By the time you do R5 is equals to I2 times this, so you also get all the voltage drop across each point. So there are two ways to analyze this. Either you use your voltage divider rule or you just use Ohm's law by multiplying your current times your resistance. In summary, we can summarize the main characteristics of a series connected circuit as being: one, the current. The current is the same through all the components in the series circuit because there is only one closed loop. So since all the components are connected in series, the current flowing through them are the same. Again, the total resistance of a DC series string is equals to the sum of all the individual resistance of each component. So all you need to do, just add all the resistance together, you will have the total resistance. Then the total voltage drop around the DC series circuit is the linear addition of the voltage drop across each component, but for AC circuit it is the vector addition. So for a DC series circuit, all you need to do, add all the voltage drop at a particular point and you get the total voltage supplied by the circuit. But for an AC circuit, it's the vector addition. But in this class, we are only going to be looking at DC circuit. So we just add all the voltage drop and we get our result. DC parallel circuit. A DC parallel circuit or a shunt connected circuit is the connection of individual electronic components which have a common voltage source across them. So when various electronic components have a common voltage source across them, we can say that they are connected in series, in parallel. For example, this is your voltage source and this is your resistor connected in parallel with this, connected in parallel with this, connected in parallel with this. So by the time you place your voltmeter between node 1 and 5 or 2 and 6 or 3 and 7 or 4 and 8, you will notice that the voltage at this point is still the voltage at this point, is still the voltage at this point, is still the voltage at this point. So in this case, we can say that the circuit is connected in parallel. The main characteristics of a parallel circuit is that they only have two nodes with each component and or source connected between these two nodes. So the circuit have only two nodes. You can see a node there. This is a node and this is a node. So what is a node? A node is a point in a circuit where two or more circuit elements are connected together, thereby serving as a junction point. So this is a node. Two circuit elements are connected here too. So the voltage drop at this point, they are all the same because they are connected in parallel. So for a parallel circuit, like you said, the voltage drop across this point is equals to the voltage drop across this point equals to the voltage drop across this point equals to the voltage drop across this point. So what changes is the current. So the total current IT flowing out of the source, when it gets to this point, will divide. Part of it will flow to I1, part of it will go straight. The same thing when it comes here, part of it will flow down, part of it will flow straight. When it comes here, part of it will flow down, part of it will flow straight. And when it gets here, it will flow down. So all we need to calculate, knowing that the current that flow through this resistor are different, so it's easier once we know the voltage drop across this particular point and we know the value of the resistance. It is easier for us to calculate our current. All we need to do, IR1, which is the current flowing through this point, is the voltage all over the resistance, which is your 24 volts divided by 10. You get your current. Also, we do that for here, we do that for here. Also, the same thing, we do that for here. The total voltage at this point is 24 volts and the resistance is 40. So by the time you do it, you are going to get the current flowing at individual point. When you add all this current together, you are going to get your total current flowing through the circuit, which is equals to this addition of all these values will give you your total current flowing through this circuit. So one key thing for a parallel circuit is to find the equivalent resistance. So to find the equivalent resistance of a parallel circuit, R equivalent is equals to 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4. In cases where the resistances are different, so you apply this law in order for you to look for the equivalent resistance. In the case of two resistors in parallel which have different resistive value, since there are only two current paths, we can find the equivalent resistance simply by multiplying the resistance and dividing the product by the sum product of the two parallel connected resistors. So for a simple case, when a circuit have only two resistors connected in parallel and they have different values, the total resistance is simply the product of the resistance all over the sum of the resistance. Very easy. When there are two resistors with different values, just say product over sum and you will get your result. But for example, find the equivalent resistance of the two resistors of 50 ohms and 75 ohms connected in parallel. So this one and this one, they are in parallel. So all you need to do, ROT is equals to product all over sum. So 50 times 75 all over 50 plus 75, you are going to get this, and you are going to have 30 ohms as your equivalent resistance. But in cases where the resistance value are all the same, the total resistance is simply the resistance value of 1 divided by 2, where 2 is equals to the number of resistance. So since both resistors are the same, just take one resistance value, then you divide by 2. Likewise, if 3 or more resistance value are the same, then the equivalent resistance will be equals to R total is equals to R over N, where R is the value of the resistor and the N is the number of individual resistors. So if you have a number of resistors in the circuit connected in parallel and each of them have the same value, you don't need to go through the long mathematics of trying to use this particular expression. All you need to say, just say R equivalent is equals to pick the value of one of the resistance and divide it by the total resistance in the circuit, and you will get your equivalent resistance. Things you must note about a parallel connected circuit: the voltage is the same across each branch component in the parallel circuit as they are all connected directly across the same voltage source. Then number 2, since there are 2 or more paths for current flow, the total current supplied by the source is the sum of all the current flowing through each parallel branch. The current through each branch can be different depending on the resistance of the branch. 3, total or equivalent resistance of a parallel circuit is less than the resistance of the smallest individual component in the circuit. This information is very key. So note that when you are looking for the equivalent resistance of a parallel circuit, the result you will get is lesser than the value of the smallest resistor in the network. So take note of that particular information. It's very key because it will guide you when you are trying to look for the equivalent resistance in a parallel circuit. So we take an example in order for to explain the combination of a series circuit and a parallel circuit connected together. So this is a simple circuit. You can see some part the circuit is connected both in series and in parallel. So using the circuit below, calculate the equivalent resistance, which is ROEQ for this particular circuit, the total current, which is IT flowing in the circuit, then the voltage level at node A and node B, then the individual branch current, which is this current here, I1 and I2, and the voltage drop across all the resistor. So to do that, the first thing we need to do is to calculate the equivalent resistance in the circuit. To do that, we start gradually. Resistor R6 and R7 are in parallel. So we resolve them first. When you resolve them in parallel, take note, when two resistors are connected in parallel, this is the equivalent resistance. So we have that R10 is equals to 1 over R6 plus 1 over R2. When we do our analysis, we get our result to be equal to 72 ohms. So that is exactly what we are getting here now. This particular part has been reduced into this part. So go forward. We notice that this part and this part that we resolve are now in series. So in series, all we need to do is just to add them together. So we have R5 plus R10 is equals to 140 ohms, which is this. Then again, all these parts, they are in series. So all we need to do, this part, they are in series. So R2 plus R3 plus R4 are in series. So by the time you add, you have 350 ohms. Again, this and this are in parallel. So by the time you resolve in parallel, we have R13 is equals to 1 over R11 plus 1 over R12. When you do your mathematics, you are going to get R13 to be equals to 100 ohms. So you can now see that R01, R13 and R8, they are all in series. So by the time you add all of them in series, you are going to get your equivalent resistance as 240 ohms. With this now, it is easy for us to calculate our current. So our total current flowing in the circuit I2 using Ohm's law is Vs over R equivalent, where Vs is the supply voltage of 120 volts and equivalent resistance is 240 ohms. When we do that analysis, we are going to get 0.5 amps at our result. Then to calculate the voltage at node A and node B is very easy. The voltage at this point, node A, is simply the supply voltage minus the voltage drop at this point, and the voltage drop at this point equals to the current times the resistance. So add our supply voltage 120 minus the voltage drop at this point. So the voltage at point node A is simply equals to 70 volts. We should also note that since the voltage at this point is 70 volts, the voltage also at this point is 70 volts, because both of them are at the same potential. There's nothing between them. So you put your voltmeter here and put here, you get the same voltage drop as this point. Okay, so the next thing we need to do is to calculate the current flowing through this part and through this part. So it is easy to do. All we need to do, we get the equivalent circuit that is there, equivalent circuit to represent that, then after which is this. Then now applying current divider rule to calculate the current flowing through this point, we use this resistor times the total current divided by this plus this. Then to calculate the current flowing through this point, to use this resistor times the total current flowing in the circuit divided by this plus this. So when we do that, I1 is equals to IT times R11 over this, we get our answer. Then I2 is equals to IT times R12 all over R11 plus R12. When we do that, we get our result. So these are total current I1 and I2. So if you add I1 and I2, you are going to get your total current IT flowing through the circuit, which is equals to 0.5 amps. The next thing for us to do is to calculate the voltage drop at each of the resistor. So now that we have known the current flowing through the circuit, we know what is I1, we know what is I2. To get the voltage drop at this point, just to multiply the current times this resistance, current times this resistance, the current times this resistance. Also to get the voltage drop, to multiply the current times this resistance. Then when it gets the current also divide, we find the current here, multiply it times this resistance, multiply it times this resistance. Or we can use other method in trying to analyze that. So first, the current flowing, voltage drop on the 100 ohms resistor, the current is 0.5 times the resistance, we get 50 volts. Then the current flowing through R2 is the current 0.147 times 75, we get 10.7 volts. Also the current flowing through R3 is the I1, which is this times 125, we get 17.9. Then the current flowing through R4 It's the same thing, 0.13 times 150 to get 21.4 volts. Then the current flowing through R5 is equals to I2 times R5, which is equals to 0.357 times 68, give us 24.3 amps. Now, the voltage drop at R6 and R7, they are the same. So all we need to do is to say VC. Our VC will simply equals to VA minus VR5 minus the voltage drop across this point. So the voltage drop across VA is 70 and voltage drop across this point is 24.3. So by the time we subtract this, we are going to get the voltage drop at this point to be 45.7 volts. So that will save us the stress of trying to look for the current through this part before trying to use the current to multiply the resistance. Then to get the current flow, the voltage drop at the 40 ohms resistor is your total current, because all the current have passed through the circuit and they are returning back to the source. So it's your total current times your resistance, which is equals to 20 volts. So to summarize, the main characteristic of combination, series and parallel circuit I define as being: 1. In the series part, the current is the same through all the components within the series string. In the parallel part, the total current is the sum of the current divided among the different parallel branches. 2. In the series part, the voltage drop across each component is different, creating voltage division. The total voltage is the same of the individual voltage drop. In a parallel part, the voltage drop across all parallel component branches is the same, and each parallel branch receives the same voltage level. 4. In the series part, the total resistance is the sum of all the individual resistances in series part of the circuit. The total resistance value is greater than the largest series resistance. So when you are trying to add resistance in series, the total resistance you will get is always greater than the resistance of the highest resistance in the circuit. Number 4, in a parallel part, the reciprocal value of the total resistance is equals to the sum of the reciprocal of the branch resistance. So for you to calculate the equivalent resistance in a parallel circuit is 1 over the reciprocal of the resistance value of each of the component. But we must know that the total resistance in a parallel circuit is always less than the smallest individual resistance in the circuit. So I want to thank you for making our time to carefully look at this lecture. And if you like this lecture, you can always leave a comment in the comment section. I want you to always like my video and always subscribe to my channel for more interesting lecture on different series. Thank you for listening.